Okay, let's just dive right in because today's explainer is, well, it's essentially a cosmic detective story, and I am so excited to share it with you. We're going to look at how a persistent, honestly infuriating noise in space, something that drove scientists absolutely crazy for years, was completely misunderstood. Instead of just being frustrating static, it turned out to be a groundbreaking, entirely new map of our own solar system. It's a perfect example of how sometimes the very thing standing in your way is actually the exact discovery you've been waiting for.
So I want you to picture this. You're an astronomer. You've pointed your highly advanced, incredibly expensive equipment out into the deep, dark universe, trying to study ancient, distant galaxies. Right? But every single time you try to get a clear picture, there's this annoying, glowing interference completely blocking your view. It's kind of like trying to look at the stars from a brightly lit city street on a really foggy night. This glowing fog was literally photobombing their images of deep space, and for a long time, astronomers just viewed it as a nuisance. It was just this obstacle they had to somehow subtract or ignore just to do their actual jobs. All right, part one, an annoying cosmic interference. Let's unpack the mystery of this glowing fog. So scientists call this interference soft X-rays. Now, when we hear the word X-rays, we usually think of, high-energy medical scans at the doctor's office. But soft X-rays are simply lower energy X-ray emissions. And for years, these soft X-rays were basically the ultimate cosmic pest. They form this diffuse, glowing background that just seemed to be everywhere. Astronomers trying to study the deep cosmos, looking at the grand, sweeping structure of the universe, found these soft X-rays were constantly muddying up their data. The big question was, where in the world, or rather, where in the universe, was this background noise actually coming from? Was it an ambient glow from the furthest reaches of space, or was it something else entirely? Well, here is where the first major clue in our detective story drops. Researchers started noticing something super weird about this soft X-ray fog. It wasn't steady. The radiation was actually fluctuating over time. And this is a massive revelation. Because think about it. If this glow is coming from distant galactic structures millions or billions of light years away, the emissions would appear completely constant to us. The sheer, mind-boggling distance would average out any changes. But because the signal was fluctuating, scientists realized, wait a minute, it can't be from deep space. It has to be a local source. This interference was coming from right here in our own cosmic backyard, our own solar system. Which brings us to part two, the eROSITA telescope investigation. The ultimate cosmic detective steps onto the scene. You see, to get a clear view of this, you have to get away from the immediate clutter of Earth. So, the eROSITA telescope was positioned at Lagrange point L2. This is an incredibly stable vantage point sitting 1.5 million kilometers away from Earth. And being situated way out there was absolutely essential. At that immense distance, eROSITA could maintain a perfectly stable, uninterrupted view of the cosmos. It allowed the telescope to cleanly isolate these specific soft X-ray signals from all the other random cosmic interference. It basically gave astronomers the ultimate high-definition vantage point. Okay, so what did eROSITA actually do once it got out there? Well, between 2019 and 2021, the telescope didn't just stare at one single spot. It conducted 4 complete continuous scans of the entire sky. Just think about the sheer massive amount of data that represents. These 4 full sweeps gave researchers the exact high-precision data they needed to trace where these local soft X-rays were strongest and how they were moving over time. And this multi-year, painstaking investigation ultimately led to a landmark paper published on April 16th in the highly prestigious journal Science. Now, what's absolutely wild about this slide is the visual proof of their success. Look closely at the comparison here. The team actually managed to completely separate the signals. On the left, you're seeing the true, unaltered cosmic X-ray sky, the deep space data that astronomers always wanted in the first place. But over on the right, you see those strange, really striking streaks. That is the isolated soft X-ray background. And here's the kicker. Those streaks aren't a glitch. They're actually a highly detailed map of our own solar neighborhood. The streaky patterns are created by variations in local emissions, combining with the specific scanning geometry of the telescope itself. By extracting the noise, they inadvertently created this stunning portrait of our local space environment. So how does this actually happen? Let's move to part 3, the solar wind mechanism. It's time for an atomic collision. It all comes down to this incredible atomic-level collision that is happening constantly all around us. Let's break it down. Step 1. Our sun is just constantly blasting out solar wind, this high-speed stream of protons, electrons, and even heavier ions like carbon and oxygen. Step 2. This highly charged solar wind travels outward until it smacks into neutral atoms just kind of resting in the high atmosphere and the heliosphere, which is the magnetic bubble protecting our solar system. Step 3. When these fast-moving charged solar ions crash into those quiet neutral atoms, a physical reaction occurs. It's called charge exchange. The heavy ions essentially steal or capture an electron from the neutral atoms. It's atomic theft. And finally, step 4, this electron capture releases a sudden burst of energy. And what form does that energy take? Yep, you guessed it, soft X-rays. That little atomic theft is the exact source of the glowing fog.
And that brings us perfectly to part 4, from obstacle to tool. This is where we finally solve the cosmic case.
The dual triumph of this mission is just brilliant. It's a total win-win. First off, by fully understanding and isolating this local charge exchange, scientists could finally subtract it from their data. They reconstructed a pristine, perfectly unaltered image of deep space emissions. They finally got that clear window they had been wanting for decades. But the real magic is the second point. The noise itself became invaluable data. They literally used it to map the solar wind. By studying the soft X-rays, they proved that the intensity of the solar wind perfectly follows the sun's natural cycle. When the sun is at its minimum activity, the solar wind and the resulting X-rays weaken. When the sun hits peak activity, the emissions surge. They were, in effect, directly watching the sun breathe through the proxy of these X-rays. How cool is that?
Talk about a plot twist, right? As researcher Gabriele Ponti so perfectly concluded, what was once an obstacle is now a precious tool for heliophysics. I mean, the very thing that generations of astronomers cursed as trash data blocking their telescopes was actually a treasure map. It provided this unprecedented, real-time way to study how our sun's solar wind interacts with the protective bubble of our heliosphere. It's just a profound reminder that in science, a simple change in perspective can turn your biggest, most annoying problem into your absolute greatest asset.
Which leaves us with this final, truly fascinating question to ponder today. How much other noise in the universe is actually hidden data just waiting to be decoded? I mean, if the annoying static blocking our view of distant galaxies turned out to be the key to understanding our very own sun, what other scientific breakthroughs are currently out there disguised as mere interference, just waiting for the right detective to look at them differently? Thank you so much for joining me in this analysis. Keep questioning, keep looking closer, and I'll see you next time as we continue to unpack the wonders of our universe.